Awesome. So yeah, welcome everyone. Today's December 3rd, and it's Kitchener-Waterloo Video Tech Meetup, and we're lucky to be joined today by Joey Parrish. Met Joey formally a few weeks/months ago at Demuxed, and he showed me a really cool demo, and he really wanted to show it at Demuxed. Unfortunately, the talk didn't get picked, but I thought it was a great idea. So yeah, take it away.
Hi, everybody. I'm Joey. I'll just jump right into the presentation here. Assuming I can find the right tab. It's normal to have like 500, right?
Yeah, 500 is rookie numbers.
Yeah. All right, here we go. The year was 1988. Sega introduced its new 16-bit system, the Genesis, aka the Mega Drive, for everybody outside of North America. This thing was on shelves for 9 years and sold 30 million units. That's even longer than Star Trek: The Next Generation was on the air. Did you know 30 million tuned in to see the finale? Coincidence? Probably. So let's get briefly into the graphics of the system. It had 12-bit color, but don't get me wrong. That's not 12 bits per channel HDR. That's 12 bits total, or 4,000 possible colors. Now, these colors get stored in one of 4 16-color palettes, where color 0 is always treated as fully transparent. So you really only get 15 colors per palette. It had 2 NTSC resolutions. There was 320 by 224 mode that has the square pixels you might expect, and the PAL equivalent mode to that was 320 by 240. It sounded odd to me, but I double checked. Corrections are welcome. An alternate resolution was available at 256 by 224 with non-square pixels that are wider than they are tall. This mode allows us to use less memory per full screen image, so we're able to fit 2 full screen images in video RAM at the same time. So, you know what you're thinking, 15 colors, 224p. Is this what people call high definition? Yes, yes it is. And all of this was good enough for Sonic. But what about video? Introducing Kinetoscope, a Sega Genesis video player. Hi, I'm Joey Parrish. You may remember me from such video tech talks as Maybe AI is a Codec and Upfish, Making Movies Fart. But today, we're going to dive into the process of building a video player for the Genesis. To start, I had to build an encoder, which is 1 part Python script and 1 part FFmpeg, because seriously, what else is there besides FFmpeg? I also had to build a player, which is mostly written in C for Sega's M68K processor, but also a little assembly for an audio driver that runs on the Sega's Z80 coprocessor. And I'm leaning heavily on an excellent open source SDK called SGDK. When you're starting from scratch with a new video format, you really have to build these 2 parts in tandem. Now, to encode a video, you have to split each frame of Rick Astley into 8x8 tiles. These tiles are native to the Sega's Video Display Processor, or VDP. Each tile has a palette number encoded into it, and each pixel is a 4-bit index into that 16-color palette. Using the non-square pixel mode, each frame takes up about 28 kilobytes out of the system's 64K of video RAM. And experimentally, I found that 10 FPS is the most that I can push uncompressed frames from main memory into video RAM. We start dropping frames at 11 frames per second, which is why I am sad to say that ours does not go to 11. Audio playback uses 13 kilohertz 8-bit PCM pushed from the Z80 coprocessor to the Yamaha sound chip using a driver that comes with SGDK. I did not write any assembly myself for this. The 8-bit limit comes from the sound chip, and the 13 kilohertz sample rate is the native rate of that particular audio driver. To wrap all of this up, I created a format that encodes everything into 3-second chunks, which is about 1 megabyte, and wraps it all up with headers with magic, version number, other metadata. Now, for a detailed look at the file format, you can check the format header in the source code. The video encoding process starts with FFmpeg to extract frames from source. Then we use FFmpeg to break those frames up into scenes so we can optimize for the limited number of colors per frame. If you were to pick an optimal palette per frame, the colors would flicker all the time and it looks awful. So doing so per scene is much better. You break the frames up into scenes and then you say this scene gets this optimal palette for all of the frames that comprise that scene. We're just using FFmpeg standard scene detection. We're not really tuning it very much. And we're also letting FFmpeg pick those colors that are optimal for that sequence of frames. Next, FFmpeg also handles the color quantization per scene and dithers each frame to use that limited palette for the scene. Finally, Python script handles the conversion of those dithered paletted frames into the tile format used by the Genesis. Audio encoding also starts with FFmpeg to extract audio samples. Then FFmpeg downmixes it to mono, normalizes the volume, and filters out any frequencies below a certain volume threshold as noise. Experimentally, this just helped with certain source content. This gives a cleaner source going into the next stage, which is a SOX plugin for FFmpeg that performs a low-pass filter to remove frequencies above the Nyquist frequency. That's half the sample rate. And then resample and dither to 8-bit audio in a way that avoids the most noticeable aliasing artifacts. I wish I could say it was completely free of those, but when you start with content that's not really made for the system, you get what you get. The final steps of the process are all in Python, where we add chunk headers, a thumbnail image, and overall metadata. The total bandwidth for this format works out to 2.4 megabits per second, regardless of the actual content. So there's no content-aware encoding for this platform. And with that, let's do a quick demo. How about a music video starring everyone's favorite red-headed British pop sensation from the 1980s? So let's get back to the slides. Now, most important thing there was that it plays. However, you may have noticed that was a very short clip on a loop. Why is that? Well, it's mainly because of the address space. What we have is a 293 kilobyte per second video stream and a 4 megabyte address space on the actual cartridge. If you set aside 110 kilobytes for the player binary, what you're left with is a maximum of 13.6 seconds of actual content. Now, that's not a lot. If you were to listen to 13.6 seconds of, say, Gangnam Style, you would get to hear Psy say Gangnam once. That's a 94% reduction in Gangnams. So what can we do? Well, let's talk about the typical cartridge. Your typical cartridge from this era has a ROM chip that's read-only memory, and it's plugged directly into the data bus and address bus of the Sega through this cartridge slot. Those pretty much plug directly into the CPU. When it boots up, it starts executing whatever instruction is at address 0 in this ROM chip. There's really not anything else going on in your typical cartridge. I mean, maybe there's a decoupling capacitor, but that's not important. What if we were to give part of the address space to static RAM and only give a small subset to the ROM? What if we add a second bank of RAM? Maybe a microcontroller? with Wi-Fi. And then the microcontroller has its own back interface to the static RAM separate from the buses that connect to the Sega. So when one bank of RAM is being read by the Sega, the other is being written to by the microcontroller with data that it's pulled down over the internet, and vice versa. In this way, you can create a potentially unlimited stream of video data and audio from the internet. So suddenly, this is a lot more than just an encoder and a player. We have custom hardware, we have firmware that runs on the microcontroller, and I even had to create an emulator so that I could do a lot of testing and development on the software, and also so that everyone at home has a chance to experience this, whether or not they have a Sega Genesis. So, would you like to see it? Sorry, this is pre-recorded. I can't hear you. Look. So this monstrosity is my latest prototype. It's composed of several boards stacked together. The reason being, I knew I was going to make mistakes, and I wanted to be able to replace one set of subcomponents at a time as I worked through the design issues in those different boards. So at the base, you have a board you can't see inside the shell, but it contains the edge connector. It also contains a flash chip that holds basically the ROM, or the player binary. After that, you have two boards, each of which is one bank of static RAM. The boards are identical except for a jumper that sets what address they respond to. And then on top here, you have a board that hosts the microcontroller. The microcontroller is a Raspberry Pi Pico, so RP2040 chipset with built-in Wi-Fi. The Wi-Fi is not always great on this microcontroller. It's good enough for IoT, but can it sustain 2.4 megabits per second? Sometimes, but not always, which is why I have this optional Ethernet adapter that plugs into the board right here. So that's the prototype. These are just a few of the failed prototype boards that I made along the way. And that's the rest of them. It was an expensive process. So the first thing that Kinetoscope does when it boots up is gets onto your network and downloads what I'm calling a catalog file. Now, this is just a file at a well-known path on the server that contains the metadata about everything else that's available to stream from this server. That's titles, it's thumbnails, and that allows the ROM to construct a menu where you can browse and decide what you want to watch. These are all of the things that I have available up on my server, which is just a cloud storage bucket. So nothing very interesting or active on the server side. So what should we watch? How about Gangnam Style? One Gangnam. Two Gangnams. That proves it. Two Gangnams was impossible with 1980s cartridge technology. Well, there's so much more that I would really love to do with this project, but I'm about out of time. Thank you very much for your time and for indulging me thus far. If you'd like to learn more, here are some links.
Oppan Gangnam Style.
Wow. That was really good.
Thank you.
Okay, I have a couple of questions, but I'll see if
Please.
anyone has any questions first, and just unmute yourself or raise your hand or whatever. Yeah, Dave.
Yeah, just a comment. While watching that, it somehow reminded me of a certain Star Trek episode where they referred to stone knives and bear skins.
Which one is that?
Oh, it's I think City on the Edge of Forever, and they're trying to build a radio out of like vacuum tubes and loose wire and stuff.
Yeah.
Perhaps a similar technological gap between today's computers and what you were working with. Anyway, that just came to mind.
Yeah, I'll see if I can find the photo that I have of one of the early stages of this, where there's a certain board that I literally just had on a breadboard connected to the rest of the system with painter's tape. And here it is, about 100 million wires on this thing. Yeah. So this is my stone knives and bear skins right here.
Well, it obviously gets an A for effort, but I'm amazed that you actually got it all working.
Eventually, yeah. It took a long time.
Still, that's impressive.
Thanks.
What was the turnaround time on the boards?
The turnaround time on the boards was usually about 2 weeks from the time I placed an order to the time it showed up in my house. And then I had to solder on the connectors that allow the stacking headers to stack it up. So,
because you showed me, I guess, the emulated version of this at DMUX, right?
Mm-hmm. Yeah.
Okay. Huh.
Yeah. So I've got a couple of boards here show what they look like when they arrive from the factory in Hong Kong. So all of the teeny tiny little ICs are put on for me by professionals because I am not that good. But then the stacking headers are surprisingly hard to source. And in fact, the ones I went to a couple of different suppliers, tried a few different varieties, and the only ones that really worked well and consistently to stack arbitrary sets of boards up, I had to buy from Adafruit and then modify. So not a fun process. And eventually I'd like to get this all into one circuit board so that you don't have to mess with any of that. It can be shipped complete from the factory, but not quite there yet.
Well, how did you burn the slides onto each of the cartridges?
So I bought these cartridges from a company called Crix, and this is the boards they send you. They're made by some random hackers in Ukraine who are really into old game consoles, and so these are rewritable flash cartridges. And then I bought the clamshells for that on eBay, and Crix also sells the programmer for their cartridges, so it has a little card slot there and USB micro on the back. And they have some software, some like .NET software to write a ROM to this. I didn't like that .NET GUI was kind of a pain in the ass to use. I ended up along the way on this project digging through their .NET source code and figuring out the serial protocol and writing a command line tool in Python. So that's yet another open source thing I published while working on this. But yeah, basically I wrote a tool that takes PDF slides and generates all of the imagery sources and uses SGDK to build a quick ROM that just lets you hit left and right on the controller to go back and forth through the slides. So there was a link to that at the end of the presentation, and then that's also linked from the Kinescope repo on GitHub.
So I just wanted to say that I think the even more impressive thing about this is that your solution would still be recognizable to people who were creating cartridges for Genesis / Mega Drive, because some of these techniques I know weren't unknown in the scene, adding additional ROMs or even additional processing on some of the later games for the system. So it's almost a future that could have been, right?
Yeah.
Someone with enough ambition could have done this in the 90s, maybe.
It's funny. There were bank switching techniques. There are a few official games that came out back in the day toward the end of that Genesis era that had some like 5 megabyte ROMs where the upper couple of megabytes could be swapped between different banks of a larger ROM chip. So you'd write to a certain address and then it would swap in. I want to say Sonic and Knuckles, I'm not sure about, but I know there was like a Street Fighter ROM that used that technique, and that technique has been extended by folks who make things like EverDrive, some of these like SD card based things to hold a bajillion games. They use some of those same techniques. What we didn't have back in the late 80s, early 90s was fast home internet and cheap microcontrollers. But what we did have back then that lived a very short life and not many people had was something called the Sega channel. I had a friend who had this at their house, and what it was your cable provider would sell you an extra subscription package and then ship you a cartridge that had a coax cable that would screw into the side of it. And it did a very similar thing to what I'm doing here, but with games, where you would have every month, there would be a different rotating selection of games that you could pick from a menu. It would download that ROM into some internal storage, and then you could play a game that, it was sort of like having a rental subscription at Blockbuster, but then like delivered to your house over your cable. And that was the closest we ever got to anything like high-speed internet in the 90s. So many times while working on this, somebody would ask me, what the hell are you doing? And I was like, but what if YouTube was invented in 1988? That's what I'm trying to do.
Could you have done ABR over Wi-Fi? Like, because you were saying like the Wi-Fi chip was flaky, right? And so part of what ABR is for is to adapt to the bandwidth of the channel, right? So
yeah, well, if there was any actual like meaningful compression happening, then yeah, but I could not come up with a reliable way to compress the frames. And then what comes down to is the CPU is basically maxed out just transferring frames to the video processor. And so the M68K can't really do any decoding or decompression. I ended up adding a compression and decompression step at the microcontroller level, because if the microcontroller can get the data off the network fast enough, it's actually a lot faster than the CPU that's in the Sega. So I came up with, I experimented with some different compression schemes. I tried LZ4, which I had used in another project many years ago because it was optimized for compression time over compression ratio. And when I tried that on the microcontroller, it was monstrously slow. Like I'm faster than gzip, but like way too slow for the thin margins I was running with on this. So what I ended up doing is just coming up with an RLE scheme. So I made my own run length encoding. Anytime you see a sequence of repeated bytes up to a certain number of bytes, it'll scan ahead. I forget, it's tunable. It'll scan ahead a few bytes, and if it starts to see a repeating pattern of bytes, either all zeros is very common, especially for quiet parts of audio or black frames, or small repeating patterns, it's able to compress those by saying, the next 3 bytes I want you to repeat 20 times or whatever. And then the microcontroller will actually execute that decompression on the fly as it's clocking those bytes out over a serial interface into the static RAM. So that all had to be sent over serial anyway. And so not expanding it in microcontroller memory was a huge savings. That was the problem with LZ4, was having to just write bytes to memory to hand you back a buffer that was decompressed. Whereas I was going to serialize it out to the RAM chips anyway. So the RLE scheme ended up being a lot faster and a lot more effective. I get something like 20 to 30% compression on, and there it really does vary by content. So some pieces of content can download at a higher effective throughput, like throughput all the way to the Sega. But it's still, at least in my living room, my Wi-Fi signal is poor enough that I get mixed results. I did some experimentation in my home office where I put all the content on my phone and set up a hotspot on my phone, connected the cartridge to the hotspot, and with that proximity and not having to relay, through a Wi-Fi router, I was able to get streaming to work over Wi-Fi pretty consistently. But mainly it's just connection quality and throughput and latency that start to eat into those margins.
And there's no there's no video scaler, right? So you have to blade on the resolution at the exact video mode, right?
And that's why I used the smallest resolution the system had too. So well, that and to be able to double buffer frames. So the player part of it is able to set up one frame at a certain address in video RAM and then say display that while it's setting up the next frame, in between vertical scans. So
I had a Super Nintendo. I didn't have a Sega Genesis, but the perceptual fidelity looks really good. Is that versus? I guess part of it is based on the color palette decisions you made, but I guess thinking back to how Sonic would look, it was very vibrant, but I'm not sure. Because you're focused just on video versus, running a game, is there basically advantages that you could take trying to just play back video and audio versus, having some game logic in there? Is there, I guess, more stressful memory, or is there something that you're leveraging more than what a typical game cartridge would have?
I think it's the opposite. I think I'm at a disadvantage because nothing is the same between frames. I mean, technically it is, but I wasn't able to take advantage of that in an algorithmic way. Whereas if you're moving sprites around a screen, you can just tell the video processor, hey, that sprite that I uploaded at this address, now I want you to display it at these coordinates. And the bandwidth between the CPU and the VDP is, for that command, is nothing. But if I am maxing it out at 280 kilobytes per second just to push frames in, I'm making that video display processor do a lot more work than it would have for a typical game. You do see some games that push those limits to the point that they actually, you can see their frame rate drop. When there's 100 rings on the screen in Sonic, when you get hit, sometimes on some of those Sonic games, you would actually see it start to go in slow motion for a second. That's tolerable in a game. And it's not tolerable in video playback. So the player does actually do some frame timing. So it gets feedback from the audio driver to see exactly what sample the audio driver's on, and then decides based on that when to send the next frame. And so based on that, I experimented with encoding at different frame rates and just seeing what it could handle. And that's how we ended up at 10 frames per second.
Would something like the 32X hardware offer any performance improvement for higher FPS or anything like that?
That's a great question. I don't know. I never had one. And at a technical level, I haven't dived deeply into what's inside there. I know that it offloads a lot of processing to, I want to say it's one of the SH chips. I forget what the processor is exactly, but they have a 32-bit processor in there that can do a lot more computation. But I think then it has to transfer everything still into the video processor. I'm not sure. Did it have its own sort of like video output? Because if not, it would still be limited by that bandwidth of getting full frames to the DDP.
Yeah, honestly, I'm not so sure. I'm trying to look at the technical specs here, and there's a whole page. It just looks like maybe an enhanced color palette, maybe twice the VRAM, and I think there's CPU improvements, but there's a lot on this page. It's hard to consume.
yeah, I'm just not that familiar with that particular device. I don't think I even knew anybody who had one back in the 90s. Like I did had a lot of Sega friends, and you know, yeah, that was just not a popular accessory.
Yeah, I think it came pretty late in the Genesis, I guess, lifespan. But
they were avoiding building the Saturn at that point.
Yeah, and I think the only game I can really remember is maybe NBA Jam Tournament Edition, and it looked maybe like marginally better than what like SNES or even base Genesis would offer.
Yeah, they had a 32X version of, I want to say, Eternal Champions or some other fighting games, but like, just didn't really take off.
Right.
Sega could build some really interesting stuff and then totally fail to market it. So a lot like Google in that way. But I remember like the Dreamcast was an incredible system. Technologically, it was ahead of its time, and it was kind of in this like weird in between generations. And then it failed, and then Nintendo put out the GameCube, which had almost all the same chips, but newer versions of the same chips that were in the Dreamcast. So it was literally ahead of its time in design.
Any other questions? Well, that was awesome. Thanks again, Joey. I know, like, just seeing all the work you've done, like, and you know, all the breadboard and that stuff. I can't imagine how long this took, but no, it's really cool. If you want to give me the links, I can
sure
pass them along.
Yeah, I started in earnest in March of this year, and then I worked out the last weird little hardware bug like a month ago. So it's it's been a process. But here, I'll put the link in the meeting chat, and
we can find all the other links that you had listed off of that link.
Yeah.
Okay.
So
awesome.
Off of the README there, you'll get links to the Sega slide generator, the Python script I used to program all the cartridges. You'll see the font that I loved so much for this, the video itself, slides, everything.
Sweet. Awesome. Well, thanks everyone for coming out. Thanks, Joey, for taking some time and all the hard work. And until next time.
Bye, y'all.
Yep. Cheers.
Thank you.
Bye.
Thanks.
Thank you. Yeah.